Hello, this is Professor Dan Kernler. This is yet another video in my statistics series. In this one, we're doing confidence intervals about the population mean. Let's get to it. Let's introduce this one with our lesbian, gay, bisexual health database. I'll put that link in the description. We're going to look at the age that the individual realized their sexual orientation. And we're going to compare different groups. So for example, I've got the age they realized their sexual orientation for gay, and then we have bisexual and then lesbians. And we can compare these and kind of wonder, all right, are the distributions different? If we look at the sample means, are those actually statistically different, or are they maybe close enough to say that they're all about at the same age? We can compute those sample means. We have 14.7 for gay men, 17.1 for bisexuals, and then 17.3 for lesbians. They're clearly different, at least at the sample level. The last two look pretty similar, but it looks like gay men recognize their sexual orientation at a younger age on average. But these are just samples. We don't know if that difference is statistically significant. The way we're going to try to answer this is we're going to try to do confidence intervals, much like we did for the population proportion. If you recall, under certain conditions, the distribution of the sample proportion will be approximately normal, with 95% within 2 standard deviations. So if we took, say, 20 different samples, then 19 of them should be within that interval, and then 1 will be without. If we drop these down and use that same width of the 95% and create confidence intervals, well, the true proportion is in the middle, and 95% or 19 out of these 20 will contain it and 1 will not. The key is that if we repeat this, about 95% of those confidence intervals will contain the true value. Now, this was for the population proportion. This is the distribution of the sample proportion, but we need the distribution of the sample mean. We need to know what is the mean of all the sample means that's in the middle and what is the standard deviation. But we have studied this before. It's the central limit theorem. The mean of all the sample means should be the same as the population mean. Shocker there. And the standard deviation of the sample means is the standard deviation of the population divided by the square root of the sample size. Now, this is always assuming that the sample size is pretty large, at least 30, or that the original variable is normally distributed. Now, we have a bit of a problem. The idea is we're trying to find a confidence interval for the sample mean. So we don't know the sample mean. How would we then know the population standard deviation? That's really unlikely. So we're going to have to substitute the sample standard deviation, but then that equal sign is not true. We can put an approximately equal to. This is really the sample standard deviation of the sample means. All right, we have to build up a little more theory here, so be patient. Remember the z-score, the number of standard deviations from the mean. If we're looking at sample means, well, then it would be x bar minus the mean of all the sample means over the standard deviation of the sample means. Again, we don't have the standard deviation of all the sample means because we don't have sigma, so we can put in its place s, the standard deviation of the sample means, but then it's not a z. The sample standard deviation is too different from the population standard deviation. In fact, this statistic that you're looking at right here has its own name. It follows what's called a T distribution, students' T distribution. There's a cool story about the gentleman who developed this, that he had to publish the paper under a pseudonym because the research that he was doing was for his company and he wasn't allowed to publish under his company name. I believe the name is William Gossett, students' T distribution. Now, because we're using the sample standard deviation there in place of the population standard deviation, then there's more uncertainty. This distribution, students' T distribution, is spread out a little bit wider than the regular normal distribution. Now, if you recall, we had this confidence interval for the population proportion, p hat plus or minus the z-score alpha over 2 times that standard deviation. We're going to do something similar now for mean, x bar plus or minus z alpha over 2 sigma x bar. Now, you might recall the confidence interval for the population proportion. It was this guy. we had this standard deviation over there was the square root of p times 1 minus p all over n. And now we are going to do the same thing for x bar. We want to do x bar plus or minus z alpha over 2 times the standard deviation of x bar, which is sigma over square root of n. But we don't have sigma, so we're going to have to use s in its place. But then we said, well, then that z is not a z, it's actually a t. And so our confidence interval becomes this guy. X bar plus or minus whatever this t is, alpha over 2 times s over square root of n. Now for the purposes of this particular video, I'm not going to actually show you how to find those critical values, that t alpha over 2, because for almost all of our examples, and any example that a statistician would find, you're going to have data, and you're going to use the data to find these confidence intervals, and you're not going to compute that by hand. You're going to use a software for that. So that's what we're going to do. We're going to use StatCrunch. I have these sample means back up here again for these 3 groups, and we have the standard deviations for each one, and we could certainly use that formula, but we're going to use StatCrunch and find the confidence intervals for these using that. Like most things in StatCrunch, this is fairly straightforward as long as you know which menu to use. Now in this case, we want to do stats and we want t-stats. We want t-stats because we're finding a confidence interval for a mean just from data. So we'll choose t-stats, one sample with data. Then we'll pick our variable. In this case, we want to do age realized. And because we want to do the different groups, we're going to group by their orientation. We'll do a confidence interval, hit compute. And then we get these 3 here that we're going to focus on. You can see there are some other groups in here, but that just became too much to put all on one slide, so I focused on the main 3 groups. If we want to visualize that, I've got a graphic up here. You can see for gay men, the interval was 14.1 to 15.2, so we're 95% confident that the real mean age realized for all gay men is somewhere in there. And then we have bisexual and lesbian. Again, what confidence intervals allow us to do is make some inferences, draw some conclusions. In this case, we can see that lesbians and bisexuals tend to realize their sexual orientation at a pretty similar average age. Whereas gay men, or gay boys in this case, I guess, would realize their age when they're still boys, much younger than lesbians and bisexuals. Now, again, we need to really emphasize the meaning here. Remember, we have this distribution of the sample means. 95% should be within here. So if I have 20 of them, 19 will be within there. One of them won't. If we draw confidence intervals, 19 of them will contain the true value and one of them won't. The key is it's 95%. If we repeat this process over and over and over, about 95% of all of the intervals that we create will contain the true population mean. All right, that is it for this one. I feel like this is another heavy video. I hope this was helpful and helped you understand the kind of the reasoning behind these confidence intervals, and then also how to calculate them in StatCrunch and then interpret their meaning once you get those intervals when you're done. If you want to see more of these, you can subscribe, hit the bell to get notified. As always, I want to thank the Elgin Community College Board of Trustees, which approved my sabbatical for the spring 2021 semester, and that's what gave me the time to record, edit, produce, and upload all of these videos for you. So thank you so much for watching, and I will see you in the next one.